Okay, so my name is Antonio. I am presenting the icing system that is going to be implemented in the surfaces of in the flight surfaces of airplanes, and this is for the final projects of software design. So why to implement this system? Because when we have the flight surfaces of the airplanes, we mostly have clear wings. So in order to the plane fly correctly, we need to provide um, the the a control system that may um, adequate the the I'm so sleepy the surfaces of in order to avoid crash and maybe miss operations. And why are we doing this? So we're modeling this in NCS scale, which is a software that we're going to cover an abstract, the requirements of high-level requirements, low-level requirements, and interface requirements also. The architecture diagrams, code implementation, analysis of results, and conclusion. Why in this sequence? Well, because the objective is to implement the icing system concerning safety regulations. As we can see in the picture, this is going to be a problem. This panel is going to be located in the cabin, and we expect that the crew can tell when the atmospheric conditions are not the optimum. The high level requirements, we have okay, I forgot to change this one. To measure the amount of ice in the surfaces, the distribution of the fuel, the de-icing fluid. That's going to cover the the wings and slats and like that. And the heating system shall be initially turned off. That's a must. And the alarm system shall be initially turned off also. What about the low-level requirements? Low-level requirements are those that represent how the implementation is going to be implemented in order to have the system working appropriately. So when we have levels below 100, and the system is going to display a blink, well, not a blink, an LED indicator that is going to indicate, is going to show that the icing condition is in that moment. So 5 seconds later, if this, sorry, 3 seconds later, if this system isn't regulating the temperature and raising the temperature of the surfaces, then the system is going to indicate with a second LED that the heating system is going to be, before that, when there is presence of ice, in that moment, and it simultaneously turns on, activates a system that is going to distribute the de-icing system, the de-icing fuel, not the icing fluid, sorry. And 3 seconds later, if this is not enough, then it's going to come in another system that is the heating system, which has an electrical resistor that is going to increase the temperature. And if these two systems are not sufficient or not enough, then an alarm is going to start beeping 3 seconds, no, sorry, 5 seconds later. That's what it says. No, sorry, 5 seconds to initiate a heating system, and 3 more to have the alarm in activated. So what are the interface requirements? These are basically only the colors and the name of the labels. So we have an white. The first one is white, then yellow, green, and red. Where is red? Where is red? Yeah, I changed this alarm because I didn't have a buzzer in my home. So I changed it to a red LED, but I didn't change in the requirements, in interface requirements, and also the names: ice label, fluid label, heating system, and the alarm system. So these are the requirements in a traceability matrix. Basically, we have the measurement system that is going to indicate whether the icing conditions are present in that moment. And we have low-level requirements associated to this and um, non-functional requirements also, which are basically these ones, the interface. Also for the distribution system, that is the de-icing fluid, the heating system. This means the electrical resistor, and the alarm. The alarm is going to make a bleep, but I changed this because I didn't have a buzzer and I didn't know. So I had to change it. I had no time. What else? We have the use case diagram. This is basically how the interaction indicates the interaction between the parts of the system, basically subsystems that are working simultaneously in order to turn on LEDs. So this is basically only one big system, that is indicating system, that has data. We're going to say data, but it's not actually data. Incoming from from other subsystems. The subsystems, as I mentioned them, they are measuring system, uh, the icing fluid distribution system, the heating system, and what is the other one? The alarm system. They are here, and basically we covered each one of them. We gave them like I I gave them like a definition inside the detection of ice, and for each of these cases, use cases. So the white LED is going to indicate the presence of ice. The blue, I didn't change this one. I thought I had a blue LED, but then it exploded. I didn't know it didn't work. And the red LED is going to be the alarm, and the heating system is going to be yellow, but I didn't have knowledge of these colors in my available components until I was back home. So I didn't know this one. And so the crew is going to know when either one of the systems is being activated. Then we have the VDD diagram. This the block definition diagram indicates the integration of all the systems interconnected. So we have the temperature sensor that is going to have a temperature in the input, and it's going to pass its data to, well, this variable. It's supposed to be data in a more developed project and a better in a more advanced version of this. But right now we only have like this CPU, which corresponds to the Arduino board, and is going to give the it's going to pass the measurement of the temperature sensor to either one of the other subsystems, sorry. So we have the indication system that is going to turn the LEDs corresponding to heating, alarm. I changed this one. I was supposed to work with another LED to indicate that the system is on, but I didn't use this one. The white LED and the yellow LED. So this is the indicating system, but we also have like well, if this system is going to be actually implemented in an airplane, we're going to have mechanical systems that are going to be distributing with pumps, and also the resistor. So we have actually this part of the system that is going to be like the distribution of the fluid. The also this I changed this. because the initial requirements in the what is the name in the in the assignment, it says that I could use an hot air pump, but I didn't use it. I only continue working with the resistance, electrical resistance. So these are the same, and the LED heating. So we have the alarm and all the subsystems working in, as a group. The IBD diagram, it just means internal block diagrams. This is like inside this block. So this only has a general overview, but this is actually how it is going to be implemented, how all the components are going to working, and how's the logic mm, going to going to work. So we have a temperature, and if this temperature coming from the sensor is less than 100, I didn't investigate this value because I didn't know what is the temperature at which the ice starts to cover the surface of the airplane. But I only used this value, which is 100. It goes from 0 to 1023, corresponding to 10 bits of the DAC, analog digital converter. And if this temperature is less than this value, 100, which is like 10%, then the ice LED and the fluid LED are going to be turned on because they're going to change the value to true. And if not, they're going to be false, so they're going to stay turned off, shut down. This value indicates that there is ice in the surface, so this flag is going to be turned on all the time when this condition is met. And we also have this second part, which corresponds to the heating LED. This is the subsystem that is turning on the electrical resistor. Basically, when we have a time that is greater than 3 seconds, that is the time that it takes to start to activate this subsystem. If this subsystem is checking the time and it's above 3 or more seconds, and we have ice in the surface, then we're going to turn on the heating LED and also like all the subsystem the electrical subsystem that corresponds to this indicating subsystem, because all this subsystem, my entire subsystem that I'm working on is a subsystem that is indicating subsystem. I want to make it very clear because I'm not integrating a full system. I don't have like the control. I don't have regulating the temperature. I didn't use any of those parts. So all I am doing is turning on LEDs to indicate what part of the process is being applied in that moment. And also, if the time that I think this one should have another input from this logic comparator, but I didn't know. I think this one has an input from here too, because if this is true and this is true, then blah blah blah. But I don't know if I should have to change this value to 5. I don't know, maybe. So if the subsystem has been indicating, if the measurement system has been indicating that the presence of ice for more than 8 seconds, that is 3 plus 5, then it is going to turn on the alarm and it's going to turn off only, like we can see in this and competitors and logic gates. These two subsystems are going to turn off when the temperature rises above 100. So if the temperature rises above 100, then it's going to turn off all these subsystems, the LEDs, and that. What is the code going to do? This code is implemented from the ANSYS subsystem, ANSYS suite, and we basically have to call this extern C library and include Deshielo, Deicing. I didn't change the names to English, sorry. And this is the name of the file of the project in ANSYS. So we're going to make use of this IVD diagram, and we're taking the names temp, ice LED, and ice range, time, heating LED. We're going to take all of these names in a structure that is an input structure and an output structure. The input structure only takes the temperature value, and the output structure, sorry, um, contains all the ports, all the pins that are going to be outputs in the Arduino board. So the so we're going to connect these pins. I didn't know we can't use pins 0 and 1. They are they have a restriction. I didn't know this. They have a restriction for use in this kind of implementation from another software, because they're going to take values for TX and RX. So they're receiving and transmitting. So we cannot use them. And it took me like maybe 2 hours to figure it out. So we're using pins 2, 3, 4, and 5 for the pins to connect the LEDs. And we have this time that is going to turn on, it's going to start counting when we have a signal. I'm going to explain this later, but this is a time that is going to take in terms of they are ticks in ticks. So the ticks are basically small pulses that are going to be counted by some function. There is a function in Arduino that can count the amount of ticks. A tick is a beep, 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 beep every time the processor does an operation. So the millis function takes this value, and we can divide it by 1000 to obtain the amount of seconds that have passed since the beginning of the code, or since one specific moment that we want to consider. And I'm going to use this later. So I want to make it very clear that this is not part of ANSYS escape system. I don't know if it can count like cheating, because I'm not using the time variable here. I am not implementing a counter um, to add 1 to the count every second. So I'm not like time equals time plus 1 every second. I'm not actually counting the time in ANSYS. I did it in the C code. Again, I don't know if this is cheating, but I don't know. It was very difficult to comply with the requirements in the original requirements, because these are like this is my interpretation of the requirements. This is the low level requirements I established in this part. This is my interpretation. This is my proposal solution. This is not something that was in the original assignment. It didn't say anything. After 5 seconds, there is going to be another system that is going to come in to work, and after three more, sorry, and after whatever, and after 3 seconds, the other system is going to turn off to indicate the alarm for excessive amounts of ice. It didn't say this, but I had to figure out a solution, a proposal to have these values, because when I was implementing the sensors, well, you're going to see this later in the video. But yeah, so I had to use something. I didn't know what, but this is like not part of the assignment. This is not, yeah, I only want to make it very clear. And what else? We have these two flags, one for the heating system when it's being activated, and one for the alarm, and they're going to turn on. They're going to be false at the beginning. And the setup This is only putting setting all the outputs and putting them to low levels. Okay. What else? This is the loop. In the wood loop, in the loop code, we have as I mentioned, the temperature sensor is going to be part of the input structure that comes from ANSYS skate. So we're taking this value temp from here and we're implementing it as in an input structure. And we're going to say that this is going to be the analog read in an analog pin in the Arduino. Um, we're initializing this yellow. This yellow, as I mentioned, this is the name of the IBD diagram. So we're implementing this IBD diagram with the input structures that are the inputs of the Arduino board, and the outputs that are going to be the LEDs because there are outputs in the board. And we're printing all the time the temperature. And okay, I think I cut a part of the code here because it was supposed to print. Okay, never mind. I think yeah, I cut a part of the code. And it's going to print the temperature and it's going to print whether it's going to be ice or not. It's going to be indicated by 1 or 0. So we're resetting everything, all the input, all the outputs. So we're going to put them to 0. If the temperature is greater than 100, this means there is no ice. And this is the cheating part because we're starting a time flag. This timer is going to count from the moment that the code indicates there is no ice. It is going to say, okay, right now there is no ice. And if in one moment we have ice again, we're going to turn this flag again, and we're going to count the time that is passing as the system reads presence of ice. We're going to talk about it later, but we're only saying that this start time equals 0 means that there is no ice, and we're resetting this flag. And these two flags for heating and alarm activated systems, they're going to be turned off because there's no use in activating them. And this is the part that indicates when the temperature is less or equal to 100. Again, this is not the value of the temperature. This is not in Celsius degrees. This is not in Fahrenheit degrees. It's only a value. And it's going to start taking the millis function. This is going to take when it's going to start this moment. And it says, okay, right now there is ice. And I need to know if in 5 seconds there is going to be, in 3 seconds, after I activate what is the name? The deicing fuel, hit a blurry face. After I activate the fluid de-icing fluid distribution, if it is not enough to rise the temperature to a value of above 100, then I'm going to need to apply the second system, that is the heating system. So I need to take this moment and start counting 3 seconds. If 3 seconds happen between this moment and another measurement, and in this interval of 3 seconds, the temperature continues being less than 100, then we need to activate the second subsystem. So this second subsystem is going to come on with no, yeah, this is going to turn on the two LEDs at the beginning because it indicates that there's the presence of ice, and then we're simulating the this error, this condition of no rising temperature when we're not when the de-icing fluid distribution system is not enough to rise the temperature, then it's going to come in another subsystem, as I mentioned, and we're going to turn on the subsystem for heating, the heating subsystem, and we indicate that it's already activated. So what is the condition to make this happen? We need the heating activated flag is turned off because it's supposed to be only one subsystem at a time. That is the distribution system. And we also need that the start time is not 0 because it's going to count 0, 1, 2, 3, 4, 5, all the way to 3,000 milliseconds. So it needs to start with a count. It needs to indicate that the previous system is not the further system is not activated yet, and also that the difference between the millis function and um, as the time passes by is going to be an interval, and this difference between the millis function that is going to take the next value of time in which the temperature is less than 100, and this starting time that we set at the beginning, if the difference is less is greater than 3 seconds, then it's going to take the signal, the subsystem, it's going to be activated. And it's going to be the same for the next subsystem, that is the alarm. But in that part, we're going to set this time to another 5 seconds, which makes 8. And we need to deactivate to have the heating system activated and the alarm deactivated. When is the heating system activated? In this moment. If the flag enters in this point, then we obviously know the presence of ice. We know that the ice detection system is turned on, and also the icing fluid, YMSC fuel, the icing fluid distribution system is also on, and that the heating system is activated, and everything is like on, indicating the presence of ice and that the temperature is not rising. So the alarm is going to again, there's no alarm, it's only a red LED, but it's the same logic. We take the millis function to the next point. If the temperature is greater than that, because we're meeting this condition, that the flag of the heating system is activated, and we only turn on the alarm. That's it. It's the same logic, exactly the same logic. And we need a delay of 200 milliseconds to go between measurements. This is part of the code that is going to be provided, because I think I didn't mention it. Where is it? Here it is. When we use ANSYS escape code in the IVD diagram, we have an option to generate code. So this part of the code is going to determine, as when we implement the blocks, we tell the system this is going to be an int 8 variable, this is going to be a boolean, this is going to be an int 16 variable, and so ANSYS escape is going to provide another code, an auxiliary code that is going to be implemented in Arduino board by means of Arduino IED. So we have this input structure that corresponds to the temperature sensor, and we have output structure that corresponds to the pins that we're implementing, the ice range, the ice LED, fluid LED. I think this is a previous version of, yeah, let me check this. Okay, I don't know why I didn't take a screenshot when I implemented this alarm system and the heating system LEDs, only the first two, I think. Yeah, ice and fluid. But in the later version of this code, These two subsystems are also indicated there. I just didn't notice this before. So this is the integration system. I'm going to explain this in English. Okay, so in this part, what we're doing is measuring. Okay, we're measuring the values obtained by the Arduino board by means of the ADC, sorry. And if these values are greater than 100, again, I am using my potentiometer to indicate the temperature because I didn't have a temperature sensor, I didn't know. And this value goes from 0 to 1023, corresponding to 10 bits. Again, back to 0. And when we have that temperature below 100, well, a value of temperature corresponding to less than 100, the two first LEDs turn on, indicating the presence of ice. Okay, there I'm going to, yeah, there is going to be 100, exactly 100. A value above 100 is going to turn off the LEDs, the LEDs, and values below are going to turn on. So there is a value above 100. We know it because they are turned off. So we lower this value and they turn on. And 3 seconds later, the third LED that represents the heating system is going to turn on, but it didn't because we compensated the value of the temperature and indicated that the icing fluid distribution system was enough to raise the temperature to a value above 100. And again, we're doing a second test with a value that is going to take 3 seconds, and then it turns on. And then 5 seconds later, it's going to turn on the alarm, indicating that it's not enough to raise the temperature to an appropriate value of temperature. And there is ice. The first LED indicates there is ice. So there is ice, and we're using all the subsystems that we have available to raise the temperature, and they're not enough. So we're saying the temperature value is still 50, and we're raising value, I think. Yeah, I am raising it. I think so, or maybe not. I don't know what I'm doing. Yeah, it's 50. Somebody tell this guy to do what I say. Okay, we're raising it already to value of 900. Sorry, 90, 99, 900, and the value of 100 is going to turn off. Well, 101 is going to turn off the LEDs because there is no ice. So there is again ice, and the first two subsystems are enough, are sufficient, but only if I think this is enough of the code. This is enough to show the demonstration. These are my references, the previous works provided by some of my classmates. This is from my from a team in the course. This is from another team in which I was taking part. I didn't work with them, but yeah, they provided me their work, so I could finish this. Um, another document provided by Professor Goretti, and a handbook of the of ANSYS documentation with the norm DO178C, which I had to look for it on internet because it wasn't provided. And that's it. Thank you very much. I think I'm recording already.